Hi, in this video we are going to talk about flow network properties. So, let's get started. Basically, the first and maybe the most important constraint or property is the so-called capacity constraint. So for all UV vertices in this given G graph, in the G graph we represented all the vertices, so the set of the vertices with this capital V. So we have the UV vertices in this capital V. We know for certain that the F flow, so the F UV, and we have these U and V arguments. Basically, we define an edge with the help of two vertices. So there's an edge between the vertex U and vertex V, and we assign a flow to this edge. And basically, this flow cannot exceed the capacity. This is what we have been discussing. So the flow cannot be greater than the capacity. Okay, FUV is smaller or equal to the CUV. It means that the flow for that given edge must be smaller or equal to the capacity assigned to that given edge. Okay, we have already talked about it in the previous video. What about the second property? This is the so-called flow conservation property. So for all the V vertices in the G graph with the V set of vertices, except for vertex S and vertex T, so basically the source and the sink, the flow income must be equal to the outgoing flow. What does it mean? If you are familiar with higher mathematics or physics, the divergence of the vector field is equal to 0 in this case. So basically we just have to sum the flow of the vertices UV, we have to sum it over all the V parameters, and it's going to be equal to null. Okay, what about the skew symmetry? It is important when we want to prove the lemmas and the theorems, for example, the maximum flow minimum cut theorem and so on. So basically it states that for all the UV vertices in the V vertices set, the flow UV is equal to the minus flow VU. So basically if there's an edge pointing from U to V, then the flow assigned to this given edge is equal to the minus FVU. It means that there's an edge pointing from V to U. We can assign the same flow, but we have to multiply it with -1. Okay. And the so-called flow constraints, that the flow leaving from S must be equal to the flow arriving at T. S is the source, T is the sink basically. And we are able to write this constraint with the help of a sum like this. So sum U FSU is equal to the sum V over FVT. So basically the flow conservation means that we have, for example, a given node. This is the node A. We have 4 edges. A single edge is pointing to this node or vertex A. It has a capacity 10 and a flow 3. And basically there are 3 edges coming out from this vertex A. One with capacity 9 and flow 1. The second edge is going out from vertex A, has the capacity 15 and the flow 1. And the last edge coming out from vertex A has the capacity 4 and the flow 1. Okay, so let's calculate the incoming flow to vertex A. There's just a single edge going into the direction of the vertex A with the flow 3. So the incoming flow is equal to 3. What about the outgoing flow from vertex A? We have a 1 unit flow going out from A, then another 1 unit going out from vertex A, and another 1 unit going out from vertex A. What does it mean? That the incoming flow is equal to the outgoing flow. And basically this is the so-called flow conservation, that for all V vertices in V, except for S and T, the flow income must be equal to the outgoing flow. So basically if we sum all the edges with all the flows, then it should yield 0. And this is exactly what's happening here. Okay, and basically what's very important that this flow conservation is not going to be true for the source and for the sink. Let's consider it. For example, as far as the source is concerned, there's going to be one edge with the flow 4 and another edge with the flow 3. So basically from the source, there's 7 unit flow going out from this source. But okay, basically this is why this is the source, because the flow is going out from this given source. What about this T? If you calculate that how many flows are going in the direction of the T, we can come to the conclusion that 6 plus 1, so 7 units of flow is going in the direction of the sink. Okay, it's quite good because this T has a divergence smaller than 0, which means that it's going to get these flows and nothing happens. Okay, so it is a valid flow network, as you can see. We have to check it when every single node except for the S and the T, we can check whether the incoming flows are equal to the outgoing flows. Let's check it here. Okay, 4 plus 2 is equal to 6. And we have a single edge with flow 6 that's going out from this node A. What about this node B? We have 3 coming in and 1 coming in. So basically it is 3 plus 1, which is 4. And 2 coming out and 2 coming out. So basically 4 unit of flow is coming in and 4 unit of flow is going out. What about this C1? 6 is coming in. Plus 1 is coming in, 1 is going out, and 6 is going out. Okay, as well, the incoming flow is equal to the outgoing flow. What about the D? 2 is coming in, and 1 is going out, plus 1 is going out, so 1 plus 1 is equal to 2. So basically this is a valid flow network, and it satisfies the capacity constraint. What is the capacity constraint? That the capacities are always greater for every single edge than the given flow. Okay, the flow may be equal than the given capacity, it is allowed, but it cannot be greater. I mean, the flow cannot be greater than the capacity, and it satisfies the flow conservation as we have seen. And what's very important, that if we calculate that what's the outgoing flow for the source vertex, it is 4 plus 3. Okay, so because 7 units are coming from the source S, that's why 7 units must go to the sink T. And we have 6 plus 1, so 7 flow is going in the direction of the sink. And this property has to be true as well. So if we have, for example, 7 units of flow coming out from this S, then we must have 7 units of flows going in the direction of the sink. Okay, and basically it is a valid network flow because this is exactly what's happening. So the flow of the network is the flow coming from S or the flow going to T. So okay, you may pose the question that we know that how to calculate the flow of the given edges, but what do we mean when we say that the flow of the given network? And the flow of the given network is the sum of flows as far as the source is concerned, or because it is equal to the sink, that's why we can sum up the flows as far as the edges are concerned that's going in the direction of the sink. And the max flow problem is we want to maximize that flow. That okay, if we are able to construct, for example, a flow network that's going to have, for example, 4 out of 4 and 5 out of 5, so maybe we are able to produce 9 units of flow, then we have to check it whether it is feasible or not. So it's very important that in the maximum flow problem, we are looking for the maximum flow that can go out from the source or go into the sink. Okay, thanks for watching.